Hello there, welcome to this tutorial on incline plane problems, how you can solve most of them. Let's say we want to look at an incline plane, so let's draw it out. Here we have, one second, let me just change to pen. So we can draw it out first. Here we are. It's not going to be the best drawing, I admit, but we draw it out first, and then one second. Next thing we want is the box, obviously the particle on there. And then the next part we want to do is the weight force. There we are, which we can call mg, for mass times by gravity. That's vertically downwards from the center of mass of that particle. Now this particle, it's a single point. It's like a point like this, a point. It's not an actual mass necessarily. Sorry, it's not necessarily a complicated geometry. It's just treated as a single point. So there's no actual shape or geometry to it when we look at these problems. Although we have drawn a box there, it still is just it was still actually be in real life a point that has a weight. That is literal. It is, and the point is of mass m, and then gravity, it gets mass times by gravity, because force times by acceleration is mass times by gravity. Right, that's the first basic part of it. If we then, however, want to do the next part, which is, let me just rub that out. For the next part, we want to zoom in a little bit, and we want to look at the normal angle that we have, which we're going to look at. I mean, the normal actually goes up vertically, perpendicular to the plane. I apologize. That is terrible handwriting. Let me just write that again in an easier way for it to be more understandable. It's not grey still, but one second. That should be going vertically upwards, like vertically upwards from the plane, because it's a normal angle. And if you have a normal angle, it's the point from the contact force from that, which is there. And on the plane, that is going to be at angle theta, which we'll call it theta for this. You can call it anything you want, but we'll call it theta for this example. Now, the next part we want to do is, let's just label that normal force. Normal. It's not very good handwriting. Normal. Now, for the next part, what we want to do is we want to get the same way, but the other way direction, like this. This arrow here is going to get. That's going to be the same angle as the triangle itself, so theta again for that angle, which is very important when it comes to being able to find things. And then, of course, that for the full triangle, you have this angle, this line here as well. And as define those, it's going to be, we know that n is going to be, the normal is going to equal mass times by gravity times by cosine of the theta angle. The reason why is because it's a triangle. You can see it's cosine, and every action has an equal and opposite reaction in Newton's law. So therefore, both directions are going to be exactly the same. Both this way and this way are going to be exactly the same force, because there's no acceleration on that plane. On that plane there's no acceleration. However, there is acceleration for the other part. There is going to be acceleration for this axis, for going down the incline. There is going to be acceleration, which we're going to call A for acceleration. Now, to find that part, what we want to do is a similar process, but we want to do, we know that there is going to equal mg, one second, mass times by gravity times by sine. I apologize, it's not the best handwriting, I apologize. Sine of theta. So mg sine of theta, because again it's a triangle, and if you look at a triangle, if we look at a triangle here, let me just draw out a full one. The triangle we've got basically is, it's like this, theta. We therefore know we're going to have sine of theta. Obviously for this part here, for the bottom, for the opposite angle, we're going to have it's going to be basically the mg. We know we have mg there, therefore it's going to be mg sine of theta, and then it's going to be mg cos of theta. I apologize again, it's not the best handwriting. I haven't got the best writing tool at the minute. That will be improved in future videos. Anyway, in terms of actually defining the equation of motion, we know that F equals mass times by acceleration, Newton's law. So therefore, it's going to be mass times by acceleration is equal to mg sine of theta in that direction. In that direction on the plane, along the plane, it's going to be equal to that. And when you cancel that out, you simply get acceleration is equal to g sine of theta. That is acceleration. However, if we were now to include gravity, for example, it's going to change the context completely, because if we include gravity, we have to include the normal force. Gravity is basically, we know that, not gravity, friction is due to the coefficient of friction of the surface and the normal force. Now, the coefficient of friction is basically the coefficient of friction of the surface. In a realistic example, that just comes down to basically the surface roughness of both the parts. So you've got the particle surface roughness. I know we're treating the particle like a point here, but in reality, if we're looking at a box and we're assuming it like a particle, you would look at the roughness of the box surface and the roughness of the incline surface, and that would give you a coefficient of friction. You actually can look further into this in engineering, mechanical engineering. You can go into things like contact mechanics, and that will tell you a lot more about that stuff. But if, for example, we were to use that now, we can then look at basically that the acceleration again is going to be mass times by acceleration is equal to mass times by gravity times by sine of theta. And there's one last part, minus mu, and then the normal force, mg cosine of theta. Like that. Again, not that easy to read, I apologise, but that's mass times by acceleration is equal to mass times by gravity times by sine of theta minus the coefficient of friction times by mg times by cos of theta. That's how you get it there. And you can see we've got it so far, like that. That is the formula we have. And then if you want to get the acceleration, you simply cancel. And you can get the acceleration into a form of g, because you can see g is in common with both of them. G, and then inside the brackets, we're going to open a bracket. We're going to have sine of theta minus mu cos of theta. Again, not that clear, but that's the point. It's acceleration is equal to gravity sine of theta minus mu cos of theta. That's the general formula for it. You see it there in there. That's the general formula for the acceleration. Now, if we wanted to look at something like the position of it, we know the general formula now in that way. If we want to look at, let's say we want to look at the actual position, we know that, well, let's start with velocity. We know when it comes to things that acceleration is equal to dv by dt. It's a calculus formula. We know that for a fact. So if we wanted to then do the next part, if we wanted to continue that, what we would do dv by dt is equal to gravity sine of theta minus mu cos of theta, like that. And then if you wanted to then find out the velocity, you simply rearrange it and get it into the integral form of percent. You get it into the integral form of v0, and which is the initial velocity, and then v of dv is equal to the integral between between time now and t0. Now, t0 is going to be 0 because it starts at time equals 0. So between t and 0, we know that the initial time will be 0. So therefore, and then it's going to be g sine of theta minus mu cos of theta. And at the end, you're going to have dt. And you can basically solve most incline problems with just that. You can integrate that and you can get it into a form. Let me show you the form I can get it into. Once you integrate that, you get it into a form of v equals v0, because you had that becomes v minus v0 because of the integral, is equal to add g t and then sine of theta minus mu cos of theta. That's the general form you get it into. it's not clear, sorry, but and then with that you can do the same thing, and we know that velocity is equal to dr by dt, and you can do the same thing. You can just do the same thing. You can do again the integral between. You can do integral between r0, the initial position, which is how far it is. You define a point. It could be how far it is from the end, and then r, and then you can just do the dr and do the same, and then you integrate velocity. Sorry, you integrate. You do the same thing. You integrate the other side. It's the same thing. And once you actually work that out, you end up with a final formula for general position. It's going to equal r is equal to r0 plus v0t. From integrating v0 is going to be v0t, and then add gt squared over 2, and then the part of sine of theta minus mu cos of theta. Like, that's the general formula we have. Again, it's not that clear, but I'll spell it out to you. So we've got position r is equal to displacement, basically, is equal to the initial displacement, which may be 0. You may define it as perhaps the particle starts 10 meters along the incline. Perhaps it starts from the very the beginning. Perhaps it starts near the end. So that'll depend on that. And then v0, which may be 0 if it starts from rest. However, it may start with some velocity, times by t. Add gravity times by t squared over 2 times by sine of theta minus mu cos of theta, where mu depends on the friction, it's the coefficient of friction, which is very important in what we're looking at. So yeah, that's the way I would generally look at all these kind of problems. But yeah, thank you. Please